Okay, I can't seem to get my page straight here. All right, a common tangent. When you hear the word common, you have something that's alike. So a common tangent is just that, a line that is tangent to two circles. So the cool thing about that is it touches both circles at one spot. So these two lines, line L and line M, are called common tangents. In fact, they're called external tangents. They touch on the outside. Now, one thing we didn't talk about here is you can also have what's called internal tangents. And internal tangents look something like this. And notice they can help form new figures. So those would be internal tangents. So it's just some terminology. And the internal tangents ones used a lot with similar triangles when we work with them. But we now have some cool properties that are going to happen with tangents that we can apply. So let's get the first theorem down. This takes a little bit of time. It's the first one says the following. If a line is tangent to a circle, okay, then it is perpendicular. Remember, I'm going to use the perpendicular symbol here to the radius at the point of tangency. That's going to be abbreviation here. So when I do this, I know that this is a tangent line, and they tell me that. All I have to do, if it's not drawn in, I can draw it in. My radius to that point of tangent will always give me a right angle. So here's the deal. If given a tangent line, mark the right angle. Okay? If you're given the tangent line, mark the right angle. And if you don't draw in that radius, do so. Because if it's not there, do it. Because you're probably going to use it later. So no matter what, I'm going to have a radius to that point of tangency, and I'm always going to form a right angle. That will work every single time. The instant I do that, guys, that's going to mean right triangles. So keep that in mind too when we're working with these. Okay, now the next one's just the converse. Okay, so it's just our converse statement. It just goes a little bit differently. It goes like this. If a line is perpendicular to a radius of a circle at a point on the circle, okay, then the line is tangent to the circle. So they're saying, hey, guess what? If you're given that right angle, you're going to know, and I'm going to write the word line there, that line M is tangent to it. So, hey, if there's a right angle, we know it's going to work. So what's going to be the key takeaway here? Radius to the point of tangency forms what type of angle? Right angle. That also means diameter to the point of tangency will form a right angle. So let's mark up the diagrams and see how this works. Everyone listen to me. You will see these on ACTs. You will see these in my class on quizzes and things, so make sure you know these. So here's the first one. So assume that the lines that appear to be tangent are tangent. C is the center of the circle. Find the value of x. Alright, so this line is tangent. Oh look, I have a radius to the point of tangency. So what do we draw in? You automatically draw in that right angle. The instant you do that, can I solve for x? Yeah. For some of you, you go, oh yes, those are acute angles of a right triangle. Just go 90 minus 58. For some of you, it's better for you to think, oh yeah, all three angles add up to 180. I don't really care which one you use. Hopefully you'll make your 8 better than mine. But you can easily solve for it then, for what's missing. X is going to be 32 degrees. Not hard to do, but if you mark up your diagram, it's easy. Now on the next one, there's a couple different things you can use, but this is the one I like best. I have two tangent lines coming from the same point of tangency, but I have two radii. Alright? And don't you agree with me that these four sides make a quadrilateral? Now I have one missing angle of a quadrilateral. What does a quadrilateral's angles add up to? 360. And remember, if you forget, you can always use this formula, n minus 2 times 180. So if you need to. So instead I'm like, oh yeah, that's a quadrilateral. So I'm going to go x plus 90 plus 90 plus 130 equals 360. So you get 310 plus x equals 360. X is 50 degrees. I just think that's the coolest thing ever. Ever. Now notice the next one, I'm actually not even using the point of tangency here. I have tangent lines, and what this tells me is I'm going to end up having a regular polygon there because all those angles are the same, and notice it's tangent at the center of each one of those. So if that's the case, I can use a central angle this time. So x is the central angle of a regular polygon. Oh, I love this stuff. So we just got to go 360 divided by 5. Oh, great. That's 72 degrees. So that central angle is 72 degrees. I love math. It is so much fun. Okay, let's try the next side, some more problems.